Hi, I'm Milad. I'm here to present our work in privacy analysis of deep learning model. I did this work with collaboration of my advisor Amir and Reza Shokri from National University of Singapore. So by now we know that deep learning is a pretty powerful technique, and it's being used in a critical task, and in many tasks there are sensitive data. So in this work, our goal is to do a privacy analysis of different deep learning scenarios and learning settings. So our main objective is to somehow measure the privacy leakage of training a deep learning model on some sensitive data set. So in part, we will focus on a specific type of attacks which called membership inference attacks. And so you are familiar with the membership inference attacks from previous talks, but to train a deep learning model, we first have a data distribution. We will pick some samples from that distribution. We call it training data. We'll train our model, and then the main observation that allows membership inference attack is that deep learning models will behave differently from the samples of the training data compared to the samples of a just data distribution. And this different distribution in the output vector allows an attacker to launch an attack and identify if some specific instance was used in the training or not. And we called a sample which was part of training a member sample, and if it wasn't a part of training, it's a non-member sample. But we want to go a step forward, and we want to see what is the cause of this behavior, what will make deep learning to behave differently for these scenarios. So let's take a look at how a deep learning model will be trained. So when you define a model, your model will have a set of features, a set of parameters, and then you will define a loss function. You will use some variation of SGD algorithm to train your model. And so for this basic sample, assume we have a hypothetical scenario when we have two classes of red and blue, and you use the SGD for several steps, and then you train the model, and this green line is your decision boundary after a few steps of SGD. And let's assume we are going to the next step of the SGD algorithm. You will take the next training batch. You will add the data point. You again compute the gradient. The main idea here is that SGD is that you will always change your model parameters in the opposite direction of gradient. So your decision boundary will be changed to make the correct classification for this new data point. So, and sometimes SGD is not perfect. You will go and make some other mistake. So the SGD is an iterative algorithm. You will again do the same thing several times, and after a few iterations, you will converge to a good point, and you will be happy with your model and will use it in your training. So then next, so let's assume that after you train the model, we will have a new data point which were not part of your training data. What is the difference between these 2 points? So one main difference is that you use all of your training data points to reduce the loss. So you will have a much smaller loss between the member data points compared to the non-member data points. And as a result, the gradient vectors will have a much smaller size. So if you compute the gradients for the blue circle, you will have a smaller gradient vector compared to the case when you compute it for a non-member data point. And so this is one of the main reasons that we are going to hypothesize that leak information about the training data. And to validate so gradient will behave differently from member and non-member data. So to validate this hypothesis, we did a simple test that we compute the gradient norm for a different, for a member and non-member data point. We saw that member data points will have a much smaller gradient norm, and as a result, it shows that, okay, it confirms that member have a much smaller gradient vectors, and the non-member data points has much larger. And this allow the attacker to be able to differentiate between these 2 points and launch his membership inference attacks. So we use this idea in several deep learning settings, such as fully trained, in both white box, black box, fine-tuning, and federated learning settings. So federated learning settings is a new approach, and is going. So you are familiar with the federated learning settings. You have some collaborators. Each collaborator has a set of private training data. No one wants to share its data, and we will use some aggregator in the middle to train an aggregated model. So the first difference between a federated learning setting compared to a normal learning setting is that you have a multiple observation of the training model parameters. So we can see that, for example, your model will change its parameter from around some point in the data space, and attacker can somehow find out that there is a point in the training data set of that specific collaborator, for example. So this is the main difference this is the first difference from the federated learning setting and the normal fully trained models. So we will go one step forward, and we want to design an active attack. If the attacker is one of the elements in the federated learning setting, he can influence the learning in a way to leak more information about the training data. So we call our attack a gradient ascent attack, and the main idea is that attacker will do a gradient update, but instead of going in the opposite direction of gradient, he will go in the direction of the gradient to force the collaborator to compensate for this attack, for this change. So in a normal scenario, if the sum point is a part of the membership, part of the training data, the collaborator will compute SGD, will go in the opposite direction of the gradient, and it wants to change the decision boundary to have a correct classification. But the active attacker here will change the parameters in the opposite direction. So this is the case when you have the point in your training data set. But what will happen if that point is not in your training data set? So if the attacker will do the gradient ascent, and it will change the model parameter in the direction, but there is no point, the collaborator won't be able to compensate for this action. And as a result, something like this will happen. And so you will have a much higher loss for that points that you use to apply your attacks. And we call those attacks a set of. So the main scenario here is that attacker has a set of target points. He will apply the gradient ascent on those target points, and the goal is to increase the loss of the model and find out if that point was part of the training data of a collaborator or not. And the basic observation is that SGD will, if some point was part of the training data, SGD will compensate for this attacker, and nothing will happen, as you can see. But if it wasn't part of the training data, you can see that the model will behave different. So again, we applied this attack, and we saw that, for example, if some point wasn't part of the training data, but it was a part of attacker target set, so attacker did the gradient ascent on it, you can see that the gradient norm it will increase compared to the case that it wasn't part of the target data set. So when we compare so the attacker has an easier way of detecting that point and find out that point wasn't part of training data. And for the other points that was part of training data, we can see that our hypothesis is correct. The gradient norm won't change that much. And as a result, the gradient vector itself will be similar in both cases. So these are our main ideas of the attack. And so we applied our attacks in a different scenario. So I will give you three of the main ones here, but we have more attacks in our paper. So the first one is the fully trained models. So attacker cannot observe the training instances. He can just only observe the fully trained model, and he will compute the outputs, loss, and gradients of the model, as we explained. And he wants to use that to launch a membership inference attack. And the next, so we have two attacks in the federated settings. One is the central attack, when the attacker is on the aggregator, and he cannot observe the local person of each collaborator, but he can he can focus on each specific collaborator and just target that updates and save those targets to launch his attacks. And one other thing that a central attacker can do is can isolate the updates from each collaborator to don't let other collaborators to affect the parameters of this specific collaborator. This way, it will have an easier way to launch its attack. And the other attacker in the federated setting is the local attacker, when he cannot see the updates of the different collaborators, can only observe the updates from the central attacker. And in all of these attacks, attackers see the gradients and can compute gradients, see the outputs and the loss for all of different epochs. So by now, we saw that attacker can, in a different setting, attacker can have different observation, and he can compute different parameters from the model. So the main goal here is that attacker give this observation as an input. An attacker wants an score function to differentiate between the member and non-member. And we use, and similar to other attacks, we use a deep learning model to design this score function. We have a beautiful deep learning model, but I'm not going to explain it. So to evaluate our attacks, we use the publicly available pre-trained models. So previous work, we usually trained their own model. So when you are training your own model, you can actually somehow force your model to leak information. But since we wanted to show that these attacks are actually working in practice, so we downloaded a state-of-the-art model for these data sets, and we launched our attacks. Also, in the case that we have to learn our models, we use all command regularization techniques. We implemented our attacks in PyTorch, and we use the common data sets for these sort of attacks. So for the results, I'm going to present the two main results, but there are a lot more. So one interesting scenario is that when you have a black box setting and you say, OK, I have the model parameters. Now I can compute the output of all intermediate layers. We computed this attack for all of our data set, and we saw that there is not that much improvement comparing the case when you only see the output of the last layer and the case when you see the output of all of the intermediate layers. This led us to believe that output of last layer contains the most information about the training data, and there is not much information. There is not that much more information in the other layers. But when we compared the case when we compute the gradients, we saw that there is a big jump in the attack accuracy. So we conclude that actually gradients leaks information, and all of our hypotheses about the gradients are correct, and the attacker can use gradients to leak more information about the training data. And also, we applied our attacks in a federated learning setting, and in both local and global, and all of our active and passive attacks. And first, we saw that global attacker has much higher performance because it's obvious it has easier time, there is less interference. And we applied our gradient ascent attack, and we saw that there's a big jump from the passive attack to the gradient ascent attack. And the most powerful attack is when we combine all of our attack, gradient ascent isolating central attacker. So we saw that we can leak a lot of information from the training model. So that concludes my talk. I'm happy to get questions.
So, questions? So maybe I start, and if somebody has a question, then go to the microphone. So your paper was titled An Analysis, and you presented a lot of attacks. So I'm now wondering, can I use any of these techniques in real world? So not the machine learning part, or do you have any defenses in mind that can help you?
So the only defenses that will work eventually is differential privacy in machine learning. But the problem with differential privacy is that right now for a complex tasks, we don't get a good utility. So nobody is going to use a differentially private deep learning for a very complex task. But if you don't use any defensive techniques, you will leak information. And
Okay.
so these things are, we don't intentionally overfit our models. We use the pre-trained state-of-the-art models.
Okay. And oh yeah, there's a question.
I don't have a question, I have an objection. My name is Oliver Erlingson. We at Google have TensorFlow privacy, and we can train complex models. We have trained complex models to good utility.
So we actually try
privacy.
to apply deep learning with differential privacy on C400. The best utility we got is about 10%, something like that. And we tried different, so we can increase the privacy budget to get a better results, but we saw that, okay, if we put the, I don't know, get a good epsilon, it's not
it's difficult at the moment to tune the hyperparameters, and your mileage will definitely vary depending on how hard you can try. Having the ability to do a full exploration of the hyperparameter space helps, but also doing various other tricks. For instance, with CFAR 100, you can start with pre-trained public models and so on. So there are lots of things you can do, but this blanket statement that you can't have complex models with high accuracy is not true.
I agree. It's not easy to do, at least.
It's not easy.
Yeah,
we are working on making it easier.
Yeah.
Further questions? Okay, so let's thank the speaker again.
Sure.